Yes, now I can write the roll numbers. Roll number 4 and 18 you type again.
Good afternoon, sir.
Go from actually Shubhankar sir told me to wait up to 3:15. That's why I was waiting basically. Otherwise the class is from 3:10.
Yes, sir. Yes, sir.
Mm-hmm. I'll wait for 1 minute only. Otherwise we'll start. Let's see how many of you join. 8 people have joined. Those who have joined, type your roll number for your attendance. Okay. Okay, in the last class, we are discussing about in detail of binary paper power cycle and all. Today, basically, we'll finish up the module one or the chapter if you see the paper power cycle, and there will be a small test of you can say 20 minutes. I'll share the Google form link. Okay, so I will leave you 10 minutes before today. That means up 3:50 I will leave you, and then for we'll take the form will accept response up to 4:15 or 4:20 like that. So there will be a small brush up and test of your module 1. Is that fine? Is that clear?
Yes, sir.
Yes, sir. It's fine.
Okay. So basically two small problems are there and three theoretical conceptual questions are there. It's a small test. So let us start today. Let me share the PPT first. One sec. Can you see the PPT?
Yes, sir. Yes, sir.
Okay.
Yes,
So
sir.
today we'll discuss about the cogeneration plant and the process heat and byproduct power, all these terms. Uh, till now, we have discussed about whatever the power generation and the Rankine cycle, different modifications we have discussed, right? So the main target was to generate the power or the electricity. But here you can see from the heading that this byproduct power term. Uh, please wait. So this your byproduct power, this term you can see. So here actually the concept lies that my power, whatever I will generate, that will be my byproduct, not my main product. And this process heat will be my main product. Okay. So what is this process heat? First of all, we have to understand that. Let us let me show you this one. This is the diagram. uh, Now this diagram is very, if you see the outline, this is exactly same like the Rankine cycle. Yes, it's the operation is same, but there are few difference in the sense, here you can see the boiler, then in place of turbine it is written back pressure turbine. Okay, then in place of condenser it is written process heater. So what is this process heater? First of all, let me explain you that first, then you will understand automatically what is this back pressure turbine and all. And the pump is there, and it's a simple concept of Rankine cycle. But here what is process heat? Basically this concept comes, there are few industries, for example I should give you that your textile industries or your painting industries, okay, in some cases some your some food grains industries where the saturated steam, that means some heating is required. Basically in general, if I say simply, some heating is required. Now that heating is done by saturated steam, okay, at a desired temperature is needed for drying, that I was talking about. For any drying purpose or any heating purpose, I need some saturated steam at a particular temperature. This is very important, at a desired temperature. Say for any textile industries, I need some drying purpose, some drying process I need, and where I have to dry that textile or that particular cloth or something, some product at say 70 degrees Celsius or 80 degrees Celsius. How can I do that? Okay, so that heat basically is called basically the process heat. Okay, that heat. Now, how that heat is called the process heat? Isothermal heat rejection is desired by giving up the latent heat of saturated steam. Obviously here I told that this drying will be done with the help of saturated steam, right? Now from where the saturated steam and this drying will, this heat whatever I'm talking about, that I will get, that is nothing but from this process heater. So you just replace the concept of condenser that we have used earlier, just replace that with the help of this process heater. It is also a heat exchanger where it will give up the latent heat, but the same concept, okay, by the same concept, but the name is process heater because this latent heat is used as a process heat for a particular drying process or particular heating process. Okay, so from here the name process heating is coming. Okay, so now it, at which temperature it will be heating will be done, that is totally, someone is joining, wait. So whatever this heating will be done, that is totally at which temperature, that is totally dependent on the application. Okay, so it depends on that particular application at which temperature I need the heating. Okay, so this is basically the main task to achieve that particular temperature. Now how that can be possible? With the help of normal turbine, normal steam turbine, that is not possible. Here that are here also that is a steam turbine, but thing is that here the term back pressure turbine is coming. Why it is called back pressure turbine? So here, so up to this it is clear or not, what is the process heat, what is the process heating, and what is the process heat? It's clear or not?
Yes, sir, it's clear.
I understand.
Okay, so process heat nothing, it's some heat, okay, it's some amount of heat at a particular temperature I need that drying process or that heating process, so I have to achieve that. Okay, with the help of this back pressure turbine. So now see by how it can be achieved. By modifying initial steam temperature and your exhaust pressure of the turbine, it is possible to generate the process heat at a process heater. Okay, so now see here, if we consider this turbine, there will be some inlet point, there will be some outlet point. So inlet condition, it's okay, it can be controlled by this boiler. Okay, at which temperature and at which pressure it is fed to this turbine. But this outlet is much important. This outlet condition from this turbine is very important. Now why it is called back pressure turbine? Basically we are by modifying the initial steam pressure and the exhaust pressure, basically the exhaust pressure, that means at the point 2 exhaust pressure of the turbine, it is possible to generate the process heat. Okay, now see how it is possible. I am telling you, say for a particular example, at 70 degrees Celsius I need this amount of heat. Okay, the saturated steam I need, and that heat I basically, that latent heat I need at a particular temperature. So whenever now you consider this expansion in the turbine, say I am having 30 bar. Okay, this inlet pressure is my 30 bar and pressure is my say 300 degrees Celsius. Okay, so during expansion in the turbine, what will happen? The pressure will drop and the temperature will also drop, but how much it will drop, that you have to fix. Now how that is done? That is basically done by a PLC controlled system. Okay, that means it's a totally, it's application of sensors. Basically what is happening at the outlet, that should be recorded, that should be recorded at the inlet, and that is using that data of the your outlet of the turbine, we are controlling this inlet also. Okay, so that is basically, if you have studied the control system, the concept of control system, some basic concept, the control system is running over here in this turbine. That means what is happening at the outlet, the inlet will know. So if the inlet will know, then that will basically control this expansion process. Why it is needed to control? Because say whatever the example I gave you, 300 degree Celsius and your say your 30 bar at the inlet condition, but what I told at the outlet condition, at the outlet means this process heating I need at a particular temperature. That means say for example 70 degrees Celsius. Now I have to find out, very important line, please listen carefully. I have to find out what is the saturation pressure for this particular temperature. I repeat, what is the saturation pressure for this particular temperature. Which temperature? Say for example 70 degrees Celsius I need the heating. So for 70 degrees Celsius, what is the value of saturation pressure? That you may easily get from the steam table. So, what is the importance of that pressure, that saturation pressure? Because the turbine, this back pressure turbine will be just you're allowed to expand up to that particular pressure, but it may expand beyond that, but it here that expansion, whole expansion is not needed. Why it is not needed? Because if I expand more, this temperature will be not controlled. Whatever the heating, this process heating I need, that will be not fulfilled. So if I need at 70 degrees Celsius heating, there will be some value of saturation pressure at that particular temperature. That pressure should be that pressure level should be present at this outlet of this turbine. So basically there is some back pressure working. If it tries to expand more, it will be not there. Okay, so this control system, whatever it is, that has been not shown over here. So if you see any your that type of application in a small factory or plant, you may find it. So that control system basically controls this inlet steam flow. Okay, this inlet steam flow, just calculating and collecting the data at the outlet, what is happening. Whenever that saturation pressure is attained, then the expansion stops basically, because then only I will get 70 degrees Celsius over here for the process heating. This concept is clear or not? Tell me.
Yes, sir.
Now, if
Yes,
we
sir.
are
Yes,
having
sir.
any doubt,
Yes, sir.
let me show you the whole slide. Then I think it is written in the slide also. Condenser, here it is very simple. I have told you condenser is replaced by the process heater. You can see the function is same. Pressure, you see this line, pressure at the exhaust from the turbine is the saturation pressure corresponding to the temperature desired in the process heater. Okay, so first, which is my goal? My goal is this temperature from the process heater, at which temperature I need this saturated steam, or I need this drying or this heating. So uh, once I'm fixing this temperature depending on the application, I'm just at that point of time I can easily fix the saturation pressure at that point of temperature. So whenever I'm getting that saturation pressure, my turbine will be allowed to expand up to that particular saturation pressure. So that is written over here. Pressure at the exhaust from the turbine is the saturation pressure corresponding to the temperature desired in the process heater. This type of turbine is basically known as back pressure turbine. The back pressure name is, it may allow the turbine may expand more, but we are not going into that region. We are packing up the pressure depending on and collecting the data from the outlet of the turbine. Okay, so this is the outlet. Basically this type of plant is known as your cogeneration plant, that I think it is written in the next slide. So the concept of process heat and byproduct power. Now let me tell you byproduct power. So what is, whatever the discussion I completed, you have always seen that my main concentration was over here, right? This process heat. Okay, whatever this process heat I need for some drying purpose in just in a particular industry, that was my main goal. But from this turbine, whatever the expansion I'm having, I'm getting some work. So from that work I will get some amount of electricity. Yes, that electricity amount or that power generation will be very small, but I will get some work, because the shafts say the shaft of the turbine is rotating, because the steam is hitting the blades. So some expansion is happening. I will get some positive work from this turbine, from which I will get some electricity. So here that electricity will be used, are used basically in those type of industries for the lighting purpose throughout the plant, or the use of different types of fans. Okay, and some small electronic devices. Okay, whatever it is needed inside the plant. So that amount of electricity is not very much high. So in a single plant, you see I am getting this process heating also, and also the lighting purpose, and some the basic needs of electricity I can also manage from this single plant. So that's why basically this type of plant is known as your cogeneration plant. Okay, we are generating two things, but here what is the main product? Main product is the process heat. Power This power is my byproduct. Is that clear?
Yes, sir.
Okay.
Yes, sir.
Okay. So next, what we are having? Yes, the same thing, the concept of cogeneration. Now this is the TS plot. You can see the simple TS plot like a your normal Rankine cycle. But what is this shaded part? This shaded part is nothing but the this, see this area. Time is about 3:35. Someone is joining now. This is the problem, you know. Okay. So here you see uh, this area under TS plot, we know area under TS plot is nothing but the heat transfer, right? That several times I have discussed. So this thing, this area will give me the amount of process heat I am getting. Okay, amount of process heat I am getting, this area, because this is the heat rejection, this is the condenser pressure or the process heater, that pressure. So what is this pressure? Basically this is the that saturation pressure. So as it is a saturation pressure, you can see it is exactly lying on over here. As this pressure is my saturation pressure at this particular temperature, whatever this temperature it is, so this outlet, you see the outlet of the turbine point is exactly lying on this. Are you seeing this? Can you see this
Yes, sir.
point?
Yes, sir.
Yes, sir. Yes, sir.
Just this point will be not somewhere over here, neither somewhere over here nor somewhere over here. It will be exactly, because from this temperature value we are exactly calculating and we are controlling basically that pressure, that saturation pressure, this turbine expand during this turbine expansion process. So this point 1 knows very well what is happening at point 2. So depending on that, it is controlled. It is controlled. Which thing is controlled? Basically the steam flow from the boiler will be your control, and so that I can end up at this exactly at this 2 point. So you may ask, sir, practically is this possible? So minor deviation may be there, but it is say my pressure, the saturation pressure is, say for example I'm giving you 5.73 bar. So exactly 5.73 bar may not be achieved, but say 5.7 bar it may be achieved. So but ideally it will be exactly at this point 2. Okay, in the saturation line. This is what the which line? Saturated vapor line. So if I do the mathematical part, so this is the byproduct power cycle. You can know byproduct means my power is my byproduct over here. That's why byproduct power cycle, and process is my main product. The shaded part is my main product. Okay. Plant producing both power and process heat is known as your cogeneration plant. I've already mentioned that. When the process heat is the basic need, power is produced as the byproduct. The cycle is known as byproduct power cycle. Very simply, I have written in the slides so that it will be very easily understood by you. Now, in your book, you may find 1 page, 2 page. It is written. The same thing has been written, just explaining the same thing in by different terms, different ways. Okay, the same thing, but the concept is this one. Now you see, if I want to calculate this amount of process heat, I can easily calculate by the basic conception that this Wt is the work that I am getting. What is Wt? It is my H1 minus H2 basically. But here you see Wt multiplied by 3600. We are doing, what is the unit is then? If I am having Wt in terms of kilowatt, if I multiply with 36 say for kilojoules, if I am having some, this is my work, so kilojoules per hour, basically per hour. Okay, kilojoules per hour, left hand side whatever I am having, kilojoules per hour, by multiplying this 3600. And what is this small w? Small w is nothing but the steam flow rate. Okay, kg per hour, how much kg of steam is I'm just feeding or it is running in this cycle per hour. And this H1 minus H2 is that is the enthalpy difference that you know very well. So what is the unit of small h? Kilojoules per kg, specific enthalpy. Is there any doubt regarding these units, whatever I'm talking about?
No, sir.
What is the unit of this small h? It is my kilojoules per kg, specific enthalpy.
Yes.
Right? So kilojoules per kg multiplied by, what is this unit? Kg per hour. So what is the unit I'm having on the right hand side? Please listen carefully. Some of you are not listening carefully. H1 minus H2, the unit is kilojoules per
Sir,
kg.
kilojoule per hour will be the last unit
Yes,
in the right hand side.
because I'm multiplying which two units? Kilojoules per kg multiplied by this unit. This is what? The steam flow rate. kg per hour. So kg will cancel out, I will get kilojoules per hour, and that is nothing but the same in the left hand side. Okay, so this equation is well known to us, still I have explained from the point of view of your units. So also I can write this QH term, you can see it is my H2 minus H3, but I will multiply with this steam flow rate if I am considering this steam flow rate W amount, your kg per hour. So I have to multiply over here also. So now if I replace this W, because W is not known to me, so if I want some generalized equation, so W, if I replace from this equation to this equation, first equation, so you see in place of this W I have written QH by H2 minus H3. So from this equation you can easily calculate what is the value of QH. So WT 3600, H2 minus H3, H1 minus H2. So if I find out H1, H2 and H3, then easily I can find out this process heat or not. Tell me.
Yes, sir.
Because if I am this H1 can easily be calculated from the Mollier diagram, from the inlet condition of the turbine, right? If the pressure and temperature is given. H2, how the H2 will be calculated? How H2 will be calculated? Hmm?
Sir, from the Mollier diagram itself.
No, if you yes, from the Mollier diagram itself, it may be calculated. But you see, for this type of problem, if you are having any process heat problem, that required temperature will be given. Okay, so that required temperature of heating will be given. So that corresponding to that temperature, what is the saturation pressure, you can find out. So at that particular pressure, you can easily find out this point as well as this point from the steam table also, or you can find it out from the Mollier diagram also. That is up to you again. Is this clear? How you can find out this?
Yes, sir. Yes, sir.
It is much more
Yes,
easier.
sir.
Some tough examples I have shown in the last class in some problems, but here the problem may come from this side. Okay, that's why again and again I'm telling at which temperature the drying or heating is required. From that temperature, you may have to back calculate the pressure. Okay, pressure of this line. Okay, then you can easily calculate this 2 and 3 point. So that is basically the concept of your process heat. And lastly, I should say it in this type of cogeneration plant, the biggest loss in the power plant that is not happening over here. The biggest loss in the power plant is the condenser loss. Why? Because you see, if you think a bit, this amount of heat we are simply wasting in a normal power plant, isn't it? Because this latent heat is nothing but the waste, and to maintain the vacuum in the condenser, we need some external work or external power. So this condenser loss is the main loss or the biggest loss in the power plant, but in the cogeneration type of plant we are not having that loss. So that condenser loss is zero, you can see in any power plant. If condense is the biggest loss in any power plant is zero here, and the energy utilized is very high. Okay, because energy, this amount of energy that I used to reject in normal type of power plant, that is not happening over here. We are using that heat, and we are also using this power also. Okay, so is this concept clear about this process heating and this?
Sir, that means process heating is done with in the same turbine, and only the
Yes,
byproduct power and
turbine is
process heat
same,
is.
everything, the components are same, but thing is that why the name is back pressure turbine, we are controlling the outlet pressure of the turbine. Okay, that's why the name is the back pressure turbine.
Okay, sir.
Okay, and this heat we are using, the this latent heat, whatever it is, the rejection, that is my main product over here. And this power, small amount of power also we are getting over here, but that power is used again for the electricity, small electricity requirements of the plant. Okay, so both the things we are using. And here you can see energy, one term energy utilized. So one factor I have not mentioned, I don't know it is mentioned in your book or not. One term comes, that is the utilization factor of the cogeneration plant. What is the utilization factor? So how I can calculate that? From your basic concept, what it says, if so what should be the concept of your utilization factor of this type of cogeneration plant? Any idea?
Sir, work ratio.
Which ratio? Which ratio?
Sir, turbine work minus the pump work divided by the turbine work. Means how
Turbine
much
work
efficient?
minus the pump work divided by the turbine work. No, I'm asking about the utilization. Where I'm utilizing the energy? Over here. But we have not talked about this one. I'm interested, this amount of energy was lost, but I am utilizing this one. This WT,
Sir, this is utilized in local, you said, the drying factory
yes, that
or
is the
other.
main product over here. Now see, what is the utilization means what? Which things I'm utilizing? QH I am utilizing, WT I am utilizing. Okay, I am utilizing with respect to what? Total work input, total energy input. This is the Q1. Q1 is what? Q1 is the total energy input. Okay, and your which things are the your output over here? Earlier the
WT and QH, sir.
yes, WT and QH both. If I neglect the WP, you can take WP, but that value is very small. If I neglect the pump work, then what are the two main output? This WT and your QH or not? Tell me.
Yes, sir. Yes.
But even we take this pump work, so that also maybe it may be taken, but then WT minus WP will be there. There is nothing new in that. But my point is, what is the utilization factor? This WT plus QH divided by Q1. Okay, WT plus that means whatever energy we are utilizing divided by the total energy input to the cycle. Is that clear? In general,
Yes, sir.
I'm here again repeating, whatever the energy I'm utilizing divided by total energy input to the cycle. So you can see whatever the energy utilizing means this plus this, and if I'm just giving this Q1 amount of energy to the cycle, WT plus QH divided by the Q1. That is the utilization factor of this cogeneration plant. Okay.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
And now there will be some efficiencies of the power plant. You can read it from your book also, but still I'm showing you once. This is the HS plot. There is nothing new over here. You just see the terms, okay, one by one. This is the turbine, say steam turbine. Okay, steam is entering. Different efficiencies in thermal power plant means there are different terms in terms of efficiency. There are different components, so there are different efficiencies. Now efficiency term will come when I'm getting some output. Okay, so output by input, I'll call that as a simple efficiency. Okay, so that is the general definition of any efficiency. So now see, if this is a steam turbine, you can see some blades are there, nozzles are there. Okay, so these things will be discussed in the next class. What is this function of this nozzle and this compressible flow? We'll start compressible flow in the next class. Okay, so this WT work we are getting, that we generally show in the TS plot also, WT amount. But there are different types of losses incurred inside the turbine, right? And in some these bearings and all this. Okay, because shaft, whenever I'm having some shaft there, that should be supported by some bearings, right? So in the bearing, just in between bearing and shaft, there is some fluid means some lubricating oil. There will be some viscous friction, so there will be some loss. So considering those losses, step by step we will understand what are the efficiencies. You see, maximum or the ideal output, work output, and the actual or the internal work output from the turbine per unit mass. How I can write? WT ideal, I have discussed this earlier also, H1 minus of H2S. Okay, this loss I have discussed earlier, so I will not repeat why this line is slanting over here. So H1 minus H2S, that is the ideal process. Okay, but actually what happens, that is called actually internal output. Okay, internal output. Why the name is internal output? Because I'm subtracting some internal losses, internal frictional loss, and other loss means some heat loss means because this turbine is obviously not 100% insulated, there will be some heat loss because hot steam is entering, so some amount of heat loss will be there. So that is the other loss. So friction, and that means there may be some pressure loss also, I should say. So ideal output, that H1 minus H2S, if I subtract this amount of internal loss, okay, let us call like this internal loss. Okay, internal loss inside this turbine, that's why it is internal. Friction and other losses. Friction means between the steam and the turbine blades, that friction. So that's why this internal output will be a bit less compared to this 1 to 2s. So it will be nothing but your H1 minus of H2. That is also called WT actual. So that's why I have written actual or internal. Now actual does not mean it is okay, I am getting that amount of work at the outlet of the turbine. Outlet means at the terminal. Okay, so so let us see what are the different losses after that. So in this loss is internal. So this is my W2 actual H1 minus H2 from the thermodynamic point of view. This is the loss, some frictional loss and some heat loss and some pressure loss that is happening internally. So if I want to calculate some efficiency, that efficiency will be obviously called eta internal. Eta suffix internal will be what? H1 minus H2 divided by your H1 minus H2s. H1 minus H2 will be obviously less compared to H1 minus H2s because I have taken losses over here in the numerator. Okay, so this is all about the internal efficiency of any turbine. Okay, now whatever the output I am getting from the turbine, that is called basically brake output. So work output available in the shaft is less than internal output due to the external losses in the bearings. So this shaft is supported by the bearings obviously. So this shaft is connected to the alternator also, electrical device, that your generator. Okay, so that generator basically generates the electricity, but before that whatever is the work output available in the shaft, that is less than this WT actual also. Okay, so which loss is happening? External loss now. So that is one example I have given. The main loss is in the bearing loss, right? So the brake output or the shaft output, that is in terms of kilowatt into 3600, that means kilojoules per hour. So that brake output, even that means brake output, I think you have heard this term. If you are you're using bike, even there is a term BHP, right? So that is the brake, that is when taking all the losses, that amount of power I am getting, brake power I am getting. Is that clear? Hello?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay, so that is the brake output basically. So that actually incurs this external losses also. Okay, so internal output minus of external loss, that means this type of bearings losses. So that, so here also similarly I can write your efficiency. So that is your brake efficiency, eta suffix brake. So what is that? Kilowatt into 3600, this term means whatever the brake output I am getting finally, divided by the ideal output. Okay, always remember ideal output. So eta brake is considering both the losses basically. Okay, internal loss here also and external losses here also. So this brake output, that means this one is the brake output divided by the ideal output, this one you can see, and WS is nothing but this the mass flow rate of the steam. So if you take this ratio, you will get the brake efficiency of the turbine. Okay, coming to
Sir, the last equation is not visible, sir.
last equation is not visible.
Yes, sir. It is because of that notification that is coming, stop sharing or hide.
Now
Yes.
you can see,
Yes, sir. Yes.
now it is visible. Kilowatt into 3600, that is the brake output divided by this is my ideal output. Okay, so this is the brake efficiency basically. So now coming to the next point, it is continued. New term is my mechanical efficiency now that is related to this brake and internal. So if you take the ratio of the brake output divided by the internal output, both the terms has been explained in the last slide. If you take this ratio, you will get the mechanical efficiency, brake output divided by the internal output. Okay, so why the name is mechanical efficiency? Basically if you take this ratio, we are mainly considering this mechanical efficiency is mainly considering the mechanical losses. Okay, mechanical losses of the turbine. So this mechanical efficiency is, again I am repeating, brake output divided by the internal output. So eta mechanical is nothing but what is the brake output? We know kilowatt into 3600, that is the brake output, brake power say I am getting, divided by what is the internal output, this one. Okay, not H1 minus H2s, it is my H1 minus H2, that was my internal output. Okay, so if we take this ratio, we will get mechanical efficiency. So don't mix up three new terms. We have three new term of your efficiency we have learned. Eta of your internal efficiency, first one, second one is the brake efficiency, third one is the mechanical efficiency. Now if you correlate, you will get this your relation between these three efficiency. Brake efficiency is equals to internal efficiency multiplied by mechanical efficiency. You can check the last few, if you have noted down the last few that means last two equations of the eta internal and your eta brake, and if you have checked this one eta mechanical, this is the relation among these three efficiencies. So this is very important. If two efficiencies are given, you can calculate the third one. Okay, so here let us a small recapitulation of this three. So while the internal efficiency takes care of internal losses, This line should be clear to you. Mechanical efficiency takes care of external losses. Brake efficiency considers both the losses. Is this line clear to you? I'm repeating. If there is any doubt, please let me know.
No, sir. No.
স্যার আবার
Repeat
রিপিট
করছি.
করুন।
Internal efficiency. Let me show you. Internal efficiency means this one, first one. Okay, it is taking care of the internal losses I told. Is this clear? Is this clear or not? Internal efficiency takes care of
Yes, sir.
internal
Yes, sir.
losses.
Yes.
Brake
Yes, sir.
efficiency takes care of both the losses I just told just a few minutes back. Again I am telling you, see, this is the brake output and this is what? This is the actual output. Sorry, this is the ideal output, h1 minus h2s it is written. So whenever I am taking ideal, so ideal, next step is my actual, next step is my brake output. So it is taking internal and external both the losses or not? Brake efficiency,
হ্যাঁ বুঝতে পেরেছি।
is it clear?
Sir, the shaft
Yes,
output, it is a kilowatt into
that is
3600.
basically in terms of kilojoules per hour. Okay, it is basically kilojoules. Kilowatt means what? Kilowatt means what?
Kilojoule per second, sir.
Kilojoule per second. If I take for the 1 hour, what will be the value?
Yes, sir, into
So
3600.
that is the simple thing. That is a simple mathematics. Okay, nothing new. So you can just for your understanding, you can call it as kilowatt also. That is up to you. Okay, so this kilowatt, that is the shaft or brake output, whatever the internal and external losses, taking both. That's why here I am having the ideal one. Now what is happening in the mechanical efficiency? You see, mechanical efficiency is this one. Sorry, mechanical efficiency is what? The shaft output divided by this actual output or your internal output, whatever I should say. Okay, so here you see there is no question of your internal losses, because internal losses has already been you taken care of in this h1 minus h2 or not? Internal losses already I have taken into my account in this internal output or not?
Yes, sir. Yes, sir.
Right? Then I am coming to the brake output. So what is the difference between internal output and brake output? Only the external losses. That is the difference, nothing else. Right? So I am taking that ratio. If I am taking that ratio, so mechanical efficiency takes care of the only external losses, not internal losses. So this may come some conceptual MCQ in your gate also, if you see they have given one time. So this efficiency, only remembering this equation will not give you any result. Yes, by remembering you can calculate some for some problem, but it is very important to understand the concept also. Okay, and there is another term, your generator efficiency, that is not related to the turbine. Okay, that is the alternator efficiency. So here you can see output at the generator terminals, that means it is the electrical part I'm talking about. Output at the generator terminals divided by the brake output from the turbine. Brake output of the turbine means that is the final output from the turbine I'm getting. Now that output is fed to the alternator or the generator, and from the generator we are getting the electricity. So that electricity is, again if I calculate, that is less than this brake output. That means there is some loss. There is some loss happening in the alternator or not? Isn't it? So
Yes, sir,
that
definitely,
loss
yes, sir.
means that is the electrical loss, that is not mechanical. Yes, that may be some mechanical loss, because whenever I'm talking about alternator, there will be some coils, there will be some electrical, means there may be some your some amount of your magnetic loss, some amount of your eddy current loss, some amount of your hysteresis loss. So these are all electrical term. If you have studied electrical machines, you will be understood more. So all these type of losses are present in the alternator. Okay, so that's why this output from the generator terminals, that means that from that three-phase connection is coming the electricity. So that output is a bit less also from the brake output from the turbine. So if I take this ratio, I will get that generator efficiency. Okay, so and lastly the boiler efficiency. Boiler is a separate unit, you know. So boiler efficiency is we can write that energy utilized divided by the energy supplied. Okay, so simply we can write what is the energy utilized. That means h1 minus h4. This h1 minus h4 we know that is the basically the heat supplied by the boiler, but that is not actually heat supplied. That means the energy supplied to the boiler. How we are supplying the energy? With the help of furnace. So so what is happening in the furnace? Some fuel is burning. So what is this in the denominator? We are having wf multiplied by cv. Wf is what? the fuel burning rate. This WF is called fuel burning rate in boiler kg per hour. Say I'm using coal for a coal fired your power station. Say I'm using coal, so there is a particular rate or supply of your supply of the coal. Say your 100 kg of coal per hour. Okay, so that is basically the fuel burning rate multiplied by the calorific value of that particular coal I am using. So that is the amount of energy I am supplying. Okay, but what I am getting, H1 minus H4. That means that is the Rankine cycle, whatever I am talking about, that several times we have shown you in the TS plot. H1 minus H4 is the Q1. So that is the Q1, I know, but the energy supplied to the boiler is this much, WF into CV. Is this clear?
Yes, sir. Yes, sir.
Yes, sir.
So if we take this ratio, so actually why this is less, basically the heat loss to the surroundings, that is basically the main loss. Okay, in the boiler what is happening?
Sir,
Yes,
yes. Sir, where is the thermal efficiency? Means, is it come under internal efficiency
thermal
or?
efficiency is nothing but the internal efficiency of the turbine,
Oh,
isn't
okay,
it?
okay, okay, sir.
Let me go back to, no, there is yeah, there should not be any confusion over here. You see, if you recapitulate the term of
Yes,
the internal or your thermal efficiency, that was your H1 minus H2 divided by H. Thermal efficiency means what? Thermal
H1.
efficiency means for this plant. You are talking about the turbine or the plant? Hello? You are talking about the thermal efficiency of the
Sir,
whole.
turbine, sir, turbine.
Yes.
Hello.
Yes. If that is turbine, that is this one. That is nothing but the internal efficiency. Right?
Oh, yes, sir. Yeah, it will come under internal. Yes, sir.
Whenever I have discussed the losses in the turbines, if you have seen that lecture, you will find the same expression. You will find the same expression, that was the eta
Yeah,
turbine,
yes, sir.
turbine losses, turbine efficiency I called there. So it's the same thing, that is the internal efficiency of the turbine basically. Okay, but here we are taking different types of losses, that's
Okay,
why we are
sure.
getting different types of efficiencies. Is that fine?
Yes, sir.
Okay, still if you are having any doubt after seeing that equation, you can call me up. Okay, uh, now you see, that was the last thing I was discussing about the boiler. The main loss in the boiler, that is nothing but the heat loss to the surrounding. So that's why whatever energy I am supplying, that I am not getting at the input to the cycle, there will be some difference. So these are the main different types of efficiencies. And finally the equation is this one, the overall efficiency of the plant. If anyone asks you what is the plant efficiency, or it is also said your overall efficiency or plant efficiency, input to the plant and output from the plant, that I have to know. Output from the plant means this is the kilowatt. Okay, if I'm talking about the generator, so from the generator whatever the kilowatt I'm getting, that kilowatt basically. Okay, not from the brake output. Okay, if I are talking about the your plant, then from the plant whatever the output is nothing but the this output, that means output from the generator terminals, that output. Okay, so that kilowatt into 3600 divided by what is the input to the plant, this one or not?
Sir, fuel into its calorific
Yes,
value.
fuel
Yes, sir.
into calorific. That is the main first step, first input, first energy input to the plant, and this is the last energy output from the plant. So this is the output to divide by input. That will give me the overall efficiency of the plant, or it is also called plant efficiency. Is that clear?
Yes, sir.
So you have to study a bit, because there are different types of efficiency I have told over here. So you have to study a bit and try to solve some problems also. Today we are not having to time to solve any problems, but whatever the problems I have discussed regarding reheat cycle and regeneration concept was discussed. Okay, try to practice more and more problems. I will try to give you one assignment, so that you will be familiar to different types of problems again. Now today I will just let me share you, please wait, do not don't leave, don't leave the meeting. I'll share the link. Okay, all of you have given the attendance, right?
Yes, sir.
Yes,
Okay,
sir.
so let me share you the link of the test, and the time I'm expanding up to 4:30. I think it will be fine, right?
Yes, sir.
Please wait. I have sent you the link. Have you got the link?
Yes, sir, got it.
Okay, enter to that link and give the test. Okay, and if you feel I have to discuss more problems in the next class, then I will take a few examples problems on the next class. Otherwise, I will start the next module that I am having in my part. Okay, so so that can be discussed later also. So thank you for attending.
Just put it in.
Thank you, sir.
Thank you very much. Thank you.
Thank you, sir.